Good day, Gators. Today I wanted to talk a little bit about molecular mass and things like that. Probably don't need this on. And so let me go ahead and share the screen here. And I'm going to start this. Okay. So we're going to start, again, talking about molecular formulas and percent composition today, as well as introduce the mole. Now, when you're just looking around, there's lots of molecules around you. So here are some examples. O2, which is oxygen gas, which is what we breathe to do cell respiration to get energy. There's C28, H48, N2, O32, S4. And, well, that's keratin, which is, the protein that's in hair and in rhinoceros, the horns of rhinoceros, things like that. Then you have C8, H8, O3. Oh, that one's really good. That's vanillin. So when you have that nice vanilla flavor, that's C8, H8O3. Yay. Then there's C10, H12, O5, N5, P. And that one's adenine. So think, DNA, guanine, adenine, cytosine, thymine, the four bases of DNA, and that's adenine. Now, molecular formulas are ratios of elements that are bonded together. For example, water is the common name. The molecular formula would be H2O. And what that formula means is that there are two H's and one O, or for the full word, two hydrogens and one oxygen in every molecule. Now, if you just have H2O, that's implying one molecule of the substance. Like we've talked about this week, if you put a 3 in front of it, the 3 coefficient means you have 3 separate molecules of that substance. If you had Ca in parentheses OH2 then, the parentheses indicates a group. So that means you have a single Ca and then 2 OHs on it. If you're counting how many atoms you have there, you have a single Ca and you have 2 OHs. So, we could maybe, I don't know if there's enough room here, but we could maybe draw it where there's, what happened there? Okay, so here it comes. We could maybe draw that as a Ca, and then you could have an OH over here, and an OH over here. So, what this means is that. So the 2 is distributed to both the O and the H. There's an OH here, and there's an OH there. Now, in order to count them, we have atom inventories. And we talked about atom inventories last week. You're basically counting how many atoms are in a molecule. So for example, for H2O, there's 2 hydrogens, and there's 1 oxygen. For CH4, well, there's 1 carbon and 4 hydrogens. If you had H2SO4, 2 hydrogens, 1 sulfur, 4 oxygen. How about CaOH2? And that was the one we just showed. There was a single calcium, 2 oxygens, and 2 hydrogens. And so you could do some other ones. And so if you want to practice on those, you could practice on those as well. Now, an important skill in chemistry is being able to determine what is the mass of a molecule. And technically it is mass. Sometimes you hear it referred to as weight. I don't know, weight implies gravity and things like that. But anyway. Now, the sum of the masses of all the atoms in a compound makes up the molecular mass. And so basically it's the number of atoms of the first element times the mass of that first element, plus the number of atoms of the second element times the mass of that element, etc., for all the different elements that you have in that compound. So for example, for H2, well, not a very complex molecule. There's just, hydrogen, and there's two of them. So there's two hydrogen atoms. Using the periodic table, each hydrogen atom is 1.008 AMUs. So 2 times 1.008 is 2.016 AMUs. We could look at water. Water has your H2 in there, which we already said was 2 times 1.008, plus an additional 1 oxygen, which is 16.00 AMUs. So the total is approximately 18.016 AMUs for the whole molecule. And notice, interestingly, most of it is actually oxygen. Even though it's H2O, most of the mass is oxygen, and only a little bit of the mass is the hydrogen. Okay, you could also do H2SO4. 2 hydrogens at 1.008 AMU each, 1 sulfur now at 32.07 AMUs, and 4 oxygens at 16.00 AMUs each, so about 98.08 AMUs for the whole molecule. Now, sometimes you'll want to know, not only how much is the mass of a single atom or a molecule, but you want to know, well, what percentage of a molecule is a particular element? That could come in important in terms of, assaying things. If you want to, if you're doing mining or something like that, and a certain percentage of some substance is gold or something, how much of it is that? Is it economically viable to mine or something like that? So determine percent composition for each element. You basically take the total mass of the element divided by the total mass of the molecule, and then multiply that by 100 to get a percent. In other words, mass all the atoms of an element, and then divide the total mass of the entire molecule, and then times it by 100. And it's just the same as if you got your percentage on a quiz. The number of right answers divided by the number of wrong or total questions, and then times 100. So for example, water, H2O. Ooh, we have a fancy animation there. Like we said, it had a mass of 18.016 AMUs, which I think we figured out on the previous panel. Now, what you can do is the percent hydrogen then, you just take this mass of hydrogen, the 2.016 AMUs, and divide it by the total mass, 18.016, and then multiply that by 100, and you get 11.19% hydrogen. You can repeat that with oxygen. 16 divided by 18.016 times 100 is 88.81% oxygen. You could also just take 100 and subtract 11.19 from it and get the same answer. A second example, O2. Well, that was pretty easy because O2, there's only oxygen, so it's 31.998. If we use, this is actually more sig figs here, but if we use the additional sig figs, 15.999, the bottom line though is there's only oxygen there. So 31.998 divided by 31.998 is 1 times 100 is 100%. So yeah, oxygen is oxygen. But you might have something like this that's more complex. So Mg3PO4 2. And here, notice there's 3 magnesiums at 24.31 AMUs each. There's 2 phosphates at 30.79 AMUs each, or 61.94 AMUs for the phosphorus. And then the oxygen part of the phosphate, it's 4 times 2, or 8 oxygens. So 8 times 16.00 is 128. When we take the 72.93 for the magnesium, the 61.94 for the phosphorus, and the 128.00 for the oxygen, and add them all together, we get a total mass for this molecule, or compound, because it's ionic, of 262.87 AMUs. Then, if we wanted to find out how much magnesium is in there, you would take this mass of the magnesium, 72.93, and divide it by the total mass, 262.87, and multiply by 100, and you get 27.74% magnesium. Repeating it for the phosphorus, you'll find that it's 23.56% phosphorus, because phosphorus has a mass of 61.94 AMUs in this compound, out of the total of 262.87. This number divided by that number, and again times 100, will give you 23.56. And finally, oxygen, there's 128.00 grams, or AMUs, divided by your 262.87, and then times 100% gives you 48.70% oxygen. So surprisingly, magnesium phosphate is more oxygen than anything else. Almost half of it is oxygen, which is why oxygen actually ends up being one of the most common elements out there, because it's in all the substances that have oxygen in them, which is a surprising lot. Okay, moving on, the mole. And we're going to introduce this a little bit here and really start talking about it next week in more detail. And the cool thing about the mole is it's a quantity that allows you to convert the atomic mass. So in those previous things, I was talking about atomic mass in terms of AMUs, except one time I slipped and I said grams. But the mole allows you to then talk about atomic masses in grams. And it's a quantity. So the mass is a quantity of substance. And technically, a mole is 6.02 times 10 to the 23rd particles of a substance. And so if you have 6.02 times 10 to the 23rd particles of carbon, the mass is 12.01 grams. So instead of talking AMUs, you can now use the periodic table in grams, which is pretty important because all of a sudden that allows us to quantitatively talk chemistry. And we can do math. So let's say you had a glass of water and it had a mass of 259 grams, and you want to know how many moles is that? Well, your half is 259 grams of H2O. What you're wanting to solve is number of moles of H2O. Now, like we said on the previous part of the slides here, water has a mass of 18.016 AMUs. So we can do a one-step DA problem to solve this problem. We start with 259 grams of water. Then we say 1 mole of water divided by 18.016 grams of water, because we set up here that 1 mole is 18.016. Water is 18.016 AMUs. So a mole of it is that many grams. And as a result of that, 259 grams divided by 18.016 grams, grams will cancel, water cancels there, leaving moles of water, and that's 14.4 grams of H2O. We can go the other way. And we already talked about the mass of water. And again, this AMU, you could talk about moles per, that it's 18.016 grams per mole. We can do that as well. So the half here is 31.0 moles of H2O. Now, again, 18.016 grams of H2O is 1 mole of H2O. Setting up this way, moles of H2O cancels, and you have 31.0 times 18.016 is 550